Yeah, let's consider the mercury analysis by cold vapor atomic fluorescence. Okay, this is not a open use technique, but it is important, especially for the environmental analysis. Now, let's consider the mercury. Yeah? Mercury is very harmful element. Okay, it's everywhere. And, let's see this, a map. This is a global annual surface concentration of zero valent of mercury. Okay, this is a um, very strong blue color means a high concentration of mercury, right? It is, our nation also has a very high concentration of mercury, all right? But here, Africa or uh, South America and Oceania, the mercury concentration is quite low. Okay, mercury, zero valent mercury concentrations in the air near Earth's surface. Okay, this is a map. Mercury is also found as divalent to mercury in clouds and on particles in the atmosphere. Approximately two-thirds of atmospheric mercury comes from human activities, okay, including coal burning, waste incineration, and chlorine production by the chloralkali process. Okay. Now, question is, how do we how do we precisely measure this mercury concentration? Okay. Look at that. The unit is nanogram per cubic meter, right? So actually, this number is quite small, but it's significant. All right. Here is one method to um, measure mercury concentration. Okay, look at that. This is called cold vapor atomic fluorescence. Okay, as you see, to make atomization, you need very high temperature, at least 2000 Kelvin or maybe up to 6000 Kelvin. Okay, but here the temperature is quite low. Uh, you need only 450 degrees C. Okay, this is not a low temperature, but compared to the atomic spectroscopy, and this temperature is quite low. Okay, let's see how do we um, analyze the mercury. Okay, first here on this flask, this here is your sample inside. Okay, yeah. So you need bubbling here. Okay, and inside this flask, you um, first oxidize mercury and then reduce to mercury zero valent. Okay, then uh, bubble with argon. Okay, and this argon gas now passes first oxygen removal trap. Okay, and mercury removal trap. Okay, um, why? Mm. So since you need to reduce mercury divalent mercury here, you don't uh, have oxygen. Okay? You have to remove oxygen first, and then maybe argon may contain mercury in paper, although very small amount. But anyway, mercury should be removed by trap. Okay, it is usually gold trap is used, okay, to remove mercury. Why? Uh, see, mercury, gold very easily forms amalgam with mercury. Okay, in other words, they have those two metals have a high affinity. Gold atom uh, dissolves in mercury. Okay, so by passing through the gold trap and mercury in air should will be removed. Okay, and then now you bubble your sample, and then the zero valent of mercury now evaporate, and it goes through several traps. Okay, first sodium hydroxide and calcium oxide trap for acid fumes, and then important is two traps here, sample trap and analytical trap. Okay, now here in the sample trap, um, you see, you have gold coated silica sand, okay, and then all mercury is trapped by this gold coated silica sand. But when you um, increase temperature to 450 degrees C, mercury, yeah, uh, trapped in gold coated silica sand now released from the trap in gas form. Okay, now this gas form pass through another trap, so called analytical trap, but it is also heated at 450 degrees C. um, Actually, you need only one trap, but for the precise measurement, you need two traps: a sample trap and an analytical trap. Okay, and then here, gaseous mercury enters this fluorescence cell here. Okay, and then you need the lamp to induce fluorescence from mercury. Okay, usually you need a mercury lamp, and then the signal is amplified by this detector, photo multiplier tube. Okay, the rest the sample is the bent through this line. But here, mercury, since mercury is very harmful element, mercury should be removed from this bent. Okay, by again by gold. All right, here, so you uh, eliminate this fluorescence cell by mercury lamp here, and then at the right angle you detect this fluorescence. Okay, so in this way you can detect down to 0 0.5 nanogram per liter, okay, which is parts per trillion. Okay, extremely low concentration can be determined. All right. Okay, so to do the atomic spectroscopy, light is atomized in a flame, okay, in a very hot flame. All the compound will be destroyed and then they will be atomized, okay, or electrically heated furnace can be used, or inductively coupled plasma can be used. So there are several different ways to atomize your compound. Okay? And sensitivity and interference depend on the types of atomization. Okay, you will see soon. The first, no, the method for atomization is to use a flame. Okay, a flame is here. You need a burner. Okay, you need a burner to atomize your sample. Okay, to use this burner, you have to have fuel, oxidant, and sample. Okay, and here from the bottom of this burner, your sample is what inspirated into this burner. Okay, since the burner uh, temperature is so high, so inside the burner, although your samples are completely destroyed anyway, they are atomized. Okay, and then you measure the absorption or the emission. Okay, here this is the basic structure of a pre-mix burner. Okay, here you input oxidant and fuel here, and then sample is introduced through this line. Okay, and then here is the vapors, and this is spray chamber, and then uh, your sample is induced into this burner. Yeah, this is a burner with long, long flame, about 10 centimeters. Okay, and you need nebulization. That means you have to the the sample here, liquid sample should be broken into fine particles, yeah, small droplets of a few micrometer size. Otherwise, atomization efficiency will be quite low. Okay, so this nebulizer makes aerosol, okay, of few micrometer size. Okay? So fine Nebulizer makes a fine suspension of liquid or solid particles in a gas. Okay? So to operate this instrument, you need at least 1 to 2 millimeters. Okay, this amount of sample, you may think this is a very small amount, but actually sometimes this is too big. Okay, and then you'll see how uh, much smaller amount can be used. Okay, look at this the flame. Okay, flame has structures. Okay, this one. This is a blue. Let me see. This is a preheating region, and this is a blue cone, and then this one is the internal interconal layer, and upper part is the outer cone. Okay, so depending on which part, okay, so the temperature also different. Okay, and this is the droplet size. Okay, so using nebulization, you cannot make uniformly distributed particle size, but the particle size has some distribution. Okay, usually it has this kind of form. Okay, and then this one is maybe around several few micrometers in diameter. Okay, yeah. And depending on fuel oxidizer combination, the flame temperature also changes. Okay, for example, the fuel oxidant, this ethylene is fuel and air is oxidant. Okay, with this combination, the flame temperature can be raised to 2400 to 2700 K. Okay, if hotter flame needs, okay, um, for the high boiling elements, um, we use mixture of acetylene plus nitrous oxide, and then we can increase temperature to 3000 Kelvin. Okay, most element forms oxides or hydroxides, and then atomic spectrum becomes weak and becomes more complicated. So exact precise analysis may be hindered. Okay, so molecular molecular spectrum is very broad, should be uh, removed from the atomic spectrum. Okay, rich flame, rich means excess fuel. In this case, carbon species um, is reduces metal oxide or metal hydroxide, so sensitivity will be increased. Okay? Lean flame, this is not lean flame means excess oxidant makes hotter flame. Okay, so if you want to make hotter flame, you need lean flame. So you look at this table. It shows the maximum flame temperatures. For example, acetylene air combination temperature is rather low, but acetylene nitrous oxide and toward combination gives you a little bit higher temperature. They like that, all right. Then cyanogen, yeah, this one, and oxygen combination, you can have the temperature up to 4800 Kelvin. Wow, this is quite low, quite high temperature. Okay, so you need to maximize atomic absorption or atomic emission. In order to do that, um, you have to find an optimal condition for fuel, and oxidant, and sample. Okay, and also flow rate, right? Okay, other than using flames, you you can use furnaces to atomize your sample. Okay, furnaces, the concept is the same. You have a furnace, and then you put your sample inside the furnace, and then you increase temperature. Okay, what kind of furnace are used? Electrically heat graphite furnace is usually used. So this electrical heat graphite furnace is has greater sensitivity than flame, much better. And also, you don't need a larger volume of your sample. Okay, you need only 1 to 100 microliter. Okay, this is quite small amount compared to flame case. Okay, and temperature could be raised up to uh, this uh, uh, this temperature. Okay, 2558 degrees C to prevent oxidation of graphite. Okay, you may wonder, yeah, if you heat graphite. Graphite is made of pure carbon, and then carbon may be oxidized to carbon dioxide. So you have to prevent the oxidation of graphite. So argon gas must should be passed over furnace. Okay? So in graphite furnace, only the several second residence, okay, makes atomization, okay? And its sensitivity is better than the flame case. Okay? With a very reproducible sample injection, probably using automatic injection method, you can achieve high precision, about 1%. Yeah, this is quite good one. Okay, but you need practice. Okay, you have you need time to practice yourself. Okay? This is the um, inside picture. This is the graphite furnace, and this is droplet, and this is a pipette, and this is droplet is hanging. Okay, well, this is graphite furnace here, and injection is done through this hole, right, like that. And this one is hollow cathode lamp. Okay, light. Uh, this one generates light, and then it passes through this furnace. Okay, this is a wrong injection here because droplet is too high. So this droplet is on the floor of the furnace, and this is good injection. It says. Okay, furnace is heated in 3 or more steps to atomize the sample. Yeah? Important is atomization. For example, the ferritin, you need uh, to measure. You want to measure the ion content in ferritin. Um, the ion concentration is about 0.1 ppm, quite a low concentration. Okay, you inject 10 microliter of a sample into the furnace at 90 degrees C. Okay, and first you need to dry your sample at the elevated temperature for 20 seconds to remove solvent. Okay, and charring for 60 seconds at very high temperature 1400 degrees C to destroy organics. Charring means pyrolysis. The pyrolysis means what? Heating. uh, Heat the temperature, heat the sample in the absence of oxygen. Okay, yeah, with oxygen your sample, yeah, will be all oxidized. Okay, and then atomization is done for 10 seconds at 2100 degrees C. Okay? When ion is vaporized, the absorption reaches the maximum. Okay, right. And after atomization, furnace is heated to 25 degrees C for 3 seconds, and then all other the reduce one is removed. Okay, now here is the caution. Okay, and except for atomization step, nitrogen or argon gas uh, must flow through a furnace, okay, to remove the volatile materials. An electrical signal is the time-integrated absorbance during atomization. It is important to record that a signal as a function of time. Okay, you need to record the signal as a function of time. uh, so the analytical signal is the peak signal, yeah, at the step of atomization. Okay, yeah, this configuration is also the furnace made of the graphite, but this is transversely heated. Okay, this is structure of a transversely heated furnace. Okay, the transverse means what? Uh, well, you see, you this is a uniformly heated. What this is a platform. Okay, I think this is furnace. Then this is a platform on which your sample is to put. Yeah, light comes from this side and come out from this side, and this is a heater. Yeah, heater, and this configuration is called transversely heated. Yeah? It has a right angle. All right, and so this transversal heating system provides uniform temperature distribution over whole furnace. Okay, yeah, so this has advantage over ordinary types of furnace. Okay, and so in this way you can have uniformly heated, a furnace. All right, and so you see, in this way, uh, the wall of furnace, okay, is the wall of furnace now distribute the temperature in the inside the furnace. Okay, so absorbance will be greatly increased by total samples vaporization, okay? And also reproducibility will be improved. Okay, now let's consider atomization, flames, furnaces, and plasma. Okay? So, in order to maintain the furnace temperature uniformly, so the transversely um, heated system may be employed. Transversely means from side to side. In the meantime, longitudinal heating is from end to end. Okay, and this longitudinal heating, the center of furnace is hotter than ends. Okay, so that is not good. So in longitudinal in a furnace, the vaporized sample may be concentrated, okay, condensed, at the center part, okay, and it may hinder the next the measurement, okay, which means that the previously analyzed sample, you know, have some effects on the next analysis. That is called memory effect. Okay, memory effect. With the memory effect, uh, the analysis may not be precise. Okay? But in transversely heated furnace, this memory effect will be reduced. Okay? So there are many types of graphite. Okay? So best one is pyrolytic graphite. Okay, pyrolytic graphite. Yeah? The structure, you have a very well-defined structure. Okay, and here is a direct solid sampling. Yeah, a solid sample weighed onto graphite platform. This is platform. Directly you put the solid sample here. Okay? No sample pre-treatment due to large sample amount. Okay? No sample treatment. Pre-treatment is needed, okay, for this solid sample case. Okay, so In this way, direct solid sampling gives you lower detection limit than liquid sample. Okay? Matrix modifiers for phonics. Matrix means everything in a sample other than on a light. Okay? So matrix modified is sometimes needed to uh, reduce the analyte loss. Okay? This is additive, or it is added uh, to obtain clean separation. Okay, so matrix modifier either makes make matrix more volatile or makes analyte less volatile. Okay, so sometimes you need matrix modifiers.